Well, let me ask a question. I think this is a great place for us to start. It's usually posing an appropriate question, a question that roots out an insight for us, or at least drives our discussion forward. Will be good. And in fact, this will remind you of a question that I've asked you previously. So are NFAs, so these are non-deterministic finite automatons, are NFAs or automata, are NFAs capable of recognizing more than regular languages? Interesting question, right? Well, for a couple of reasons. The first one is that all the things we've seen so far, they sound like something conceivable that maybe I could do with a DFA. It's not quite clear at this stage what it means for a language to not be regular, really at all. We haven't discussed that idea at all. But there's a much more conceptual but interesting thing really going on here. When I say that are NFAs capable of recognizing more than regular languages, there's another way of me putting this question. So imagine I give you a DFA. So a DFA, say it's DFA D, we would agree that it has a language, right? Namely, the strings for which the DFA accepts on those strings. We would denote this as L of D, right? Likewise, if I have an NFA, say we'll call it N, we would say, oh, the language of NFA N is the set of strings for which the NFA accepts, right? And we talked about the differences between these two things previously, correct? Now, what would it mean in two different scenarios? What would this question really mean if I said yes or no? Well, if I said yes, that means that there exists some NFA N such that when I look at the language here, it has to be that the language itself, for some NFA, it has to be one such that I cannot come up and derive a DFA such that L of D isn't equal to L of N. So there has to be some NFA that is capable of this, right? It has to exist as long as there's at least one, then the answer would be yes, right? Because by definition, we said that any DFA, if I look at the language it recognizes, we said that that is a regular language, right? To say that the answer is yes to this, that would mean that there exists one NFA that does not have the same property. It means that that language has to have the property that there is no DFA. Now, if I said no, if I answered this no, what would that mean? What would that mean? Well, it could be taken a couple different ways. Well, first, we've really seen the versatility of NFAs, right? We already know that every NFA is like a generalization of a DFA, correct? So to posit this saying that it would recognize less than the regular languages would seem very strange, right? Because I already told you that non-determinism generalizes over determinism, correct? So to suggest that it would recognize less than the regular languages would be very surprising and strange, right? So if I said no, then perhaps an interesting idea would be if I were to give you an NFA that there may exist an equivalent DFA in the sense that its language is in fact the same language over here. And that's what we're going to explore here today, is we're going to be seeing how, when I give you an NFA, I can actually build a DFA that has the exact same language. Namely, surprisingly, the answer is actually no. And in fact, it is the case that all languages NFAs recognize are regular. So what we're going to do is we're going to be exploring this, namely, we're going to be exploring how NFAs and DFAs are in fact equivalent. Meaning that if I give you an NFA, there's going to exist a DFA for which the languages that they actually recognize are going to be in fact be equal. Now, you might ask, Dan, how are we going to do this? I'm going to introduce a couple different pieces that are going to get us there, to get to the claim that this is in fact true. So there's going to be a bunch of bits and pieces. And that's what we're going to be doing today, is we're going to be building up to the theorem that is going to tell us that this is going to be the case. So at the heart of proving the claim, this one, is actually a procedure. It's a rather important procedure. So let me write something down about this. At the heart of proving this claim is the subset construction. So some people call this the powerset construction. You'll see why either one is pretty common. So some people call this powerset construction instead. But I'll just refer to it as the subset construction. So before I attempt to prove this equivalency between DFAs and NFAs, I'm going to show you what the subset construction is. We're going to see an example, and then I'm going to show you how we can specialize this subset construction so that we do it a little bit smarter than just what you're going to first see. So check this out. I'm going to describe this procedure to you. So this is something you can implement. So to be clear, what we're going to be doing here is I'm going to take an NFA, N, and I'm going to show you how to build a DFA such that this holds. Now, I'm not going to prove the last part here. I'm going to first show you how to do this construction so that you take the NFA and make a DFA. And then we're going to prove that this is indeed the case. So here we go. So given NFA N, and I'm going to use some notation that's a little different than what we did previously, just to indicate that it's the NFA versus the DFA. Okay, everybody? So check this out. So we're going to have Q sub N sigma delta N Q0 and F N. I have to be very careful when I pronounce that, okay? We describe / construct a DFA D, which is going to have a set of states QD, sigma. So notice that the sigma is going to be the same as this one. It's going to have a transition function QD. It's going to have an initial state, and I'm going to make a note about this in a moment, that's going to be Q0 with curly braces around it. So that's going to indicate a subset. But I'll get to that in a moment, okay? And then we have FD. Now, where L of N is equal to L of D. So just a couple quick things before we get into this. First thing, I'm using these N's to indicate and use parts of the NFA. The D's are to help us distinguish between the two. N's for NFA, D's for DFA, okay? Is that clear, everybody? So remember, the definition of the transition function is different between n and d. So notice Qn, this is the definition of a transition function for a NFA, right? This is the transition function for a DFA. This is going to play a very important role here. So please make sure, don't forget about that. And this marker is giving me some fun time. It's gone. It's gone. Pooh. So let's describe the subset construction. So DFA D is constructed as follows. So naturally, I'm going to have to describe to you what the states are, what all of these are. So a second thing that is going to be fairly important here is that you'll notice right here that this right here is describing a subset of the states, right? So notice here's Q0, then this is Q0 with curly braces around it. What's going to happen in this construction, and we're going to see this, and it'll come very apparent when we do the example, that we're going to be having it where we're going to be building subsets of the original set of states. But the thing is that they're going to be treated like labels. So like just for example, you'd agree with me that this is the number 5, right? But you would agree with me as well that this is a number 5 on a card, right? So it's on a card. So be aware of the context that is being used here. First, it is indeed a subset of the set of states of n, right? But it's also going to be a label for a state. So states, or potentially some subset of states, that's like reading the 5 versus treating it like a state, which is like having a card here. So just don't let that throw you off, okay? So you'll see what I mean, because remember, the DFA transitions into exactly one state. It'll look a little bit weird if you don't remember this, that we're going to be constructing labels for states based on the subsets. And of course, you could always relabel these to give them names that are a little bit easier to follow. So first, we got to talk about the states of DFAD. So first, QD is the power set of Qn. So for those, just as a reminder, power set simply means all the subsets of Qn. So a question, how many states can there be then for this DFA? So we've actually talked about this previously when we talked about counting in the past. But how many subsets are there of a given set with n elements in it? So I'll let you think about it. If there are n states, there are how many? How many? Well, I'll give you a bit of a tip. Okay, for any one subset, so any one subset I determine from a set of n elements, I have the choice of either including it in the subset or not including in the subset. So there's two choices, right? But I do this for n elements. So that means that how many can there be? Well, there's exactly 2 to the power of n of them. So there's an exponential number of states in this DFA. So just as a remark, so that is a lot of states, just be very clear. That's an exponential number. It means that there's going to be a little bit of a blow up in the process of this. So, just as a remark, so any states not reachable not reachable from the start state can be discarded. Now let me explain what that means. So if you look at your transition diagram for a DFA, we agree that the machine starts in Q0, namely, well, if our DFA was this one, it would start in this subset's label, right? But likewise, we said that it starts in a start state, you process symbols, right? But there's going to be some states that no matter which string you give it, it will never actually reach one of those states, meaning it will never transition into that state at any point, period, regardless of what the string is. These are what we refer to as states that are not reachable from the start state. And hence, you can get rid of them. They're just sort of redundant. They're just sitting there doing nothing. So you could freely remove these from this construction. I'll show you after this a way of doing this without having to do it manually, meaning that I'll show you how you can modify the subset construction procedure such that you never have to worry about these non-reachable or unreachable states. So next I'm going to talk about the final states. So just keep in mind that we have that 5 tuple over there. So far we talked about what QD is, but now I have to talk about each one of them, right? With the exception of the ones that are the same, like the input symbols don't change, right? And I've explicitly told you what the start state would be, right? But so that means that I have how many other things to tell you about? The final states and also the transitions, right? So those are the only two I haven't really told you about yet. So FD is all subsets of the states of N that include at least one final state of N. So just be a bit more precise in my language, more exactly. FD is the set of sets S, which are a subset of the set of states Qn, so that S, so if I take the elements and I check them against Fn, it has to be that there's at least one element in common. So remember, in the DFA, these subsets are going to be labels for states. So lastly, we got the transitions. We got our transitions. Oh, I forgot some lights here. Let's get some lights here. There we go. There we go. Hopefully that looks a little bit nicer. So now finally we have the transitions. For each subset, so remember, we have each of these subsets of the set of states of N, and each input symbol, each symbol A among the set of input symbols, we're going to do the following. So I'm going to write it out fancy first, and then I will give you the plain language version of what I'm just saying to do. So watch this carefully. So delta D, so remember this is the transition function for the DFA D. We're saying that for that subset, remember this is a label in the context of the DFA. S on A. We're going to go through all of the states in S, and we're going to apply the transition function of the NFA for P on symbol A. That looks a little bit scary looking at first, but here's all I'm saying to do. So look at all the states. So all I'm saying is look at all the states. P in S. I have to enunciate that very carefully. And union together. Union together. All the states N, it goes to from P on symbol A. So what I'm saying is you go through all of those states, so you'll have some subset of states. You're going to look at each one of them, and you'll look at the transition function for that. You're just going to take each one of them. So you look at those states in S, and you take and lump all together the states that you get as a result of applying the transition function on P with symbol A. So this will become very clear what this is about when we see the example. So don't let this look a little spooky. That's all I'm saying to do. And remember, when you're done this process, when you figure this out, this is just another label. Because remember, it's a transition function for a DFA, right? A DFA, not an NFA. However, it uses the transition function of the NFA to figure out what label you would use. So that's how we're going to describe the subset construction. I think it'd be a good idea we see an example. So let's walk through the process of the subset construction now. So I'm going to have three states, Q0, Q1, and Q2. The start state is going to be Q0. Whenever it reads a 0 or 1, it stays in Q0 regardless. Upon reading a 1, it goes into Q1. And then finally, upon reading a 0, it goes into Q2, where Q2 is going to be a final state. So that's going to be the only final state. So let's walk through the process of applying the subset construction. So remember, this is our NFA here. So remember, this is an NFA. The goal with the subset construction is to build a DFA that accepts the same language, meaning it recognizes the same one. Meaning that, just to clarify even further, if I give you any input string, when this guy accepts the string, it will be that this DFA will also accept the very same set of strings. So let's walk through this process. It's easier, I would argue, to do and carry out the subset construction using a transition table. So I'm going to visualize it like this. However, you're welcome, if you have an intuition for it on a transition diagram, go for that. It's fine. But I personally think that it's easier to play around with this using a transition table. In fact, it's much easier to describe it that way as well. At least that's my view about it. So anyways, what I'm going to do is go through the same process of building a transition table for a DFA. So remember, the goal here is I'm going to take this NFA, I'm going to create a DFA. So this is going to be the transition table for the DFA. Is that clear, everybody? So that means I'm going to first follow through the steps. So the first thing I told you is that this DFA is going to have, for every one of the subsets of the set of states for my NFA, I'm going to have a state. So here we go. So I'm going to have the empty set, that's indeed a subset. We're going to have Q0. I must stress, remember, we talked about this being the start state, so I'm just going to indicate that it's the start state already. Don't need to do a whole lot beyond that. We're going to have Q1, Q2. So I'm just going through all the subsets with one element in them. Well, one state, to be a bit more precise. Q0, Q1. Then we'll have Q0, Q2. And then we're going to have Q1, Q2. And then we're going to have the last one, just Q0, Q1, Q2. So as I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 states for my DFA, which is exactly what you'd expect to happen, right? Because there's 3 states. So 2 to the power of 3, 8. So what else can I label in this without needing to do a whole lot of work? So I have the start state already indicated. Well, I can indicate the input symbols, right? They're the exact same ones I had for this one, just 0 and 1. What else? What else do I already know before I have to fill in these entries here? There's something I could tell really quickly as well. I know which of these states should be a final or accepting state, right? What did we say a final or accepting state is? It's any subset here that contains a final state of the NFA. Notice that any one that has Q2 in it, because Q2 is a final state, that is also a final state over here. So Q2, the subset with just Q2 in it is this one with Q0 and Q2, and also we have Q1, Q2, and then we have this one with all the, that was a weird asterisk, let me fix that. There we go. So all of the ones I've just starred there, all of these are also final states, all 4 of those. Why? Because they contain Q2, which is a final state of the NFA, right? So now that leaves us with the part I would argue takes the most time to do with the subset construction. It is building up all of our transitions here. So just remember, just like I said explaining this before, remember, these over here, this column of subsets, indeed, these are all the subsets of the states of the NFA, right? So they're just like my number 5, right? However, in the DFA, in the context for which they're being used, they're actually just like this card. Just a label with a number 5. Just like, it could be a subset, but indeed is in fact just a label that is a subset. I can always relabel these after if I wanted to. So just as long as you remember that, you'll notice very quickly that I'm going to start putting subsets in here as opposed to just a single state. In the context of how we would normally do this, what I'm going to have here are going to be subsets, but these are actually labels for states. So please remember that. So I'm just going to make that for here. Remember. Remember. I'll say, I'm just thinking of a nice way of putting this. The sets in the transition table, are labels. The set of states QD is indeed a set though, right? So remember, these are just labels. They all just label states. But that means it's still a set of states, even though the notation here makes it look like it's just like a set of sets. So I'm just going to say we can relabel the states. So if you wanted to call these states like A, B, C, D, E, F, G, H, I, and so on, you're welcome to do that. It doesn't change anything about this. However, it becomes a little bit trickier to understand how you're supposed to compute the transition function. So that's why I'm doing it like this. Normally you would go through this process as so, and you could relabel all of the states when you're done. So let's start off with this. So remember, let's go back to our definition over here of the transition. So it's important for us to see what the game plan is. So for every one of these rows, I'm going to have to look at when I read a 0 and when I read a 1. So remember over here what our definition is for the transition of our DFA. So for any one of those subsets, which remember, that's each row. So that's what I mean by subset. It's a row of our table. When I read an input symbol, this is one of the columns. What I'm saying is you look at each one of the states that would be in that subset. You read off what the transition function for the NFA says, to what states is it going to be transitioning into, maybe multiple states. And you're going to do this over all of the states in there. And whatever you end up with will be a label of a state that for which you'll transition to the state over in the appropriate row. So let's start off here. So notice very quickly that if I look at the subset empty set, what does the definition say? For each state in the empty set, I'm supposed to apply this transition function. However, you'll notice very quickly that there aren't any states in that subset, right? So these would just be transitioning to the exact same state. Nothing too terribly interesting. How about for Q0? So remember, I look at this subset. It says Q0, so it means I'm going to look at Q0 when I read a 0. When I read a 0, what set of states do I end up with? Just Q0, right? So I just have Q0. When I read a 1, however, notice if I look at Q0, I follow with my finger. Okay, 1 stays in Q0. I have another transition with a 1. It goes to Q1. So I have Q0, Q1, right? So I have Q0, Q1 over here, and Q0 right there. Notice that they're subsets, but remember, these are labels that match up with these ones, right? Because they're all states. So these are just labels. So now I have Q1 next. So when I'm in Q1, so remember, it's just one state here. Q1, when I read a 0, I go to Q2, right? That's the only state it goes to for the NFA. However, on reading a 1, notice there's no other transitions here. It would go, in fact, transition over to the state that is labeled by the subset empty set. So next, let's look at the next row, Q2. Upon reading a 0 or 1, there are none, right? So these are all transitioned to that state corresponding to the empty set. Now, let's proceed to the next row. Q0, Q1. Now we're looking at some more interesting ones because now we have it where there's more than one state. So let's apply the definition more carefully. Okay. Q0. So I have Q0, Q1. So I'm going to look at Q0 on a 0. That's Q0, right? So for the first case, when I look at Q0, it stays in Q0, correct? And then I'm supposed to perform a union with whatever it would be for Q1. So Q1, when I read a 0, is Q2, right? So notice that I've just looked at each one of these and I see what set of states it sends me to on that input symbol. So the result of this is just Q0, Q2, right? Let's do another one. Let's read a 1. Say Q0 on a 1 goes Q0, Q1. So both has Q0, Q1. Okay, how about Q1 on a 1? There's no transition out on a 1. So this is just union with the empty set, right? So that means that we're just going to end up with Q0, Q1. Now, let's look at Q0, Q2. So let's go through the same process again. So we got Q0, Q2, like a Q0 on a 0. Stays in Q0, right? So you know that's definitely in here. Q2, when I read a 0, there's nothing, right? So it's just Q0. That's it. It's the subset with Q0 in it. And then we have on a 1, Q0 is Q0, Q1. And for Q2, it will be nothing, right? So we're going to end up again with Q0, Q1. Hopefully you're understanding the process now. It's I just look at each one of these and I look at on that symbol, like if I had a 0 when I read the 0, where am I transitioning to? So I look at that for each one of these states that's inside the curly braces here. And when I do this, I'm going to take and union together all those set of states, and that represents a label for a state that it's going to transition to. That corresponds to one of the states that I have over here. So let's continue. Now we got 2 more rows, Q1, Q2. So Q1 on a 0 goes to Q2, correct? But Q2 doesn't do anything. With that, it just simply is going to kill that thread, okay? So it's just going to be on Q1, it's just going to go to Q2 on a 0. It won't do anything in the other case when it reads a 1, right? There's no transitions out of Q1 on a 1. Neither the case for Q2, correct? And lastly, we have our last row. So Q0, Q1, Q2. So for all of them, when I read a 0, Q0, actually let's do this one carefully. So when I read a 0 in Q0, I stay in Q0. So this would be the case when I read off Q0, right? When I look at Q1, see, I missed a comma there. There we go. When I read Q1, when I read a 0, it says to go to Q2, right? And when I do this with Q2, there are no transitions out of Q2 or into Q2 from itself. So there is nothing, right? So here I end up with Q0, Q2. And for a 1, let's go through the same process again. So remember, this was for Q2. So for Q0, when I read a 1, I get Q0, Q1, right? It goes to, it stays in Q0, but it also goes to Q1, right? Because we read a 1. So it goes shoo, like this. So this is for Q0. Okay, for Q1, there is no transition with a 1, and there's no transition with a 1 on Q2 either. So we end up with just Q0, Q1. Boom. So now we in fact have a transition table for a DFA. And that is the resulting DFA from the subset construction. Now, you might be staring at this and be like, Dan, that looks a little scary with all those subsets. Well, what could you do with this? So I'm going to leave this as an exercise. But what you could do is you can relabel all of these states. So instead of calling this one empty set, you can call this like A. You can call this one B, this C, this D, this E, this F, this G, and H. You can relabel all of these states. So I could when you finish, you can relabel the states and remove unreachable states. So what I'm saying is, for example, here on this one row, everywhere where you see empty set, you're going to put an A there instead. And anywhere you see empty set here, you put A. So you're just simply saying replace anywhere you see this subset in this table with B, and C and D and so on. You can go through this entire process. I have the full example in the notes. But when you've done this process, you're going to end up with a DFA that looks like this. So if you get rid of all of those states and you label them like this, you'll end up with a DFA that looks like this. I must stress that when you don't remove all of those unreachable states, it'll look like there's a lot of other stuff going on. So you'll have a start state of B. So B is the start state because this is the subset that contains Q0 only. So it'll have B, E, F. it'll look just like this, where F is the final state. Seems like an appropriate name for the final state. So I think that's all of their transitions. So 0, 1, 1, 0, 1. Yeah. So this would be what the DFA would look like if you were to go through and do this last step. It's not required for the subset construction. It's just something that if you really want to clean it up after, you're welcome to do that. But as I've described to you, there's a way to simplify this subset construction such that you already get rid of all the unreachable states. So this is the DFA as a result, where states are relabeled. And unreachable states are removed. Boom. And that's all there is to the subset construction.